Hello. We will wait for 5 minutes and then we will start. Okay. Good evening, everyone. So my name is Abhishek Munshi. I am a PMR research scholar at IIT Jodhpur. So this is a week 7 of our regarding the advanced power electronic control. So let me start. I hope it is visible. So today we will discuss about AC to AC converter and a little bit about the space vector pulse width modulation technique. So let us start with AC to AC converter. So what is basically an AC to AC converter is? In a AC to AC converter, an AC voltage controller is the converter that can controls the voltage, current, average power delivered to an AC load from an AC source. That means the input is an AC and the output is also AC. So it is controlling the AC to AC. Okay. So the principle is operation. The principle of operation is more or less similar to the mm, half wave rectifier. For example, for a single phase AC voltage controller is similar to the half wave rectifier. But here the load current contains both positive and negative half cycles instead of, in case of the half wave rectifier, we know that we have only the positive half cycle. The negative half cycle was cancelled out because during that cycle what happens, the diode was in reverse bias state. But here the positive and negative both the cycles are operated. So these type of converters are also called as cyclo converters. Okay. Now you can analyze the half wave control rectifier and you can see that in case of the half wave control rectifier we don't have the positive cycle, but here we have the positive cycle and negative cycle both. For control rectifier, if you remember that we have start from an alpha angle, right? So this is what happens in case of the half wave controlled rectifier, and this is in case of the half wave uncontrolled rectifier. Okay. So here, before moving on to that, we have to consider some observations. Okay. So observation is that the ACR here, that is S1 and S2, cannot conduct simultaneously. It have to be conduct together. It cannot be conduct simultaneously. Okay. The load voltage is same as the source voltage when either SCR is on. If anyone S1 or S2, if anyone is on, a load voltage will be same. Okay. And the load voltage will be zero, that is V0 will be zero when either of the S1 or S2 will be off. Okay. Now the switch voltage is zero when SCR is on and it's equal to the source voltage Vs. Okay. And the final is that average current in the source and load is zero if the SCR are on in equal interval of time. If this one is on and this one is on for the same period of time, suppose this is T1 and T2, if T1 equal to T2, then the average current in the source, that is the IS, would be zero. Okay. Now, from here, if you see, when S1 conducts, the positive half cycle of the source will work. During positive half cycle, this S1 will on. Now, in case of when S2 is on during the negative half cycle, then this half cycle of output will be fine. Okay, so this is similar to that of the half wave rectifier, but here the negative cycle will be also available. So that is why it behaves like an AC. If you are averaging it, it will have a positive cycle and it will have a negative cycle, right? So that is why it will behave like an AC signal. Okay. So that's why it is called an AC to AC controller or converter. Okay. Now we have to calculate the basic equations. So for the period of time, considering this from the waveform, if it is clear that it is on from alpha to pi and then pi plus alpha to 2 pi. So if we integrate, the RMS will be Vm by root 2. If this is my Vm, Vm by root 2, root over of 1 minus alpha by pi plus sine 2 alpha by 2 pi. So kindly remember this formula and note it down. V0 RMS by R will be the I0 and the power factor will be 1 minus alpha by pi power factor. This is my cos phi. Okay. Now this alpha will be 0 for an uncontrolled resistive load and power factor will be greater than 0 for the power factor will be, if 1, then alpha will be 0, and if power factor will be less than 1, then alpha will be greater than 0. In that case, it is less than 0. If power factor is 1, then alpha is 0. So it is cleared from this equation. Okay. So if you have any doubt for the resistive load, you can ask. After which we will move into the RL load. Fine. Similarly, if we change from R load to RL load, if you change it from R load to RL load, then it can be seen that as in case of the half wave rectifier, for RL load, we remember that it will goes like this, right? It conducts a little bit for the negative half cycle. So similarly here, we will have the positive half cycle like that, and we will also have the negative half cycle since it is an AC controller. Okay. So for RL load, this will be the output waveform. Okay, for current. So here the I naught will be Vm by Z sine omega t minus theta for the period of time alpha to omega t beta, that is for this period of time, and it will be 0 from beta to pi. Okay. So the theta will be tan theta inverse omega L by R. So finalize, we will get this is the equation of the output current up to beta. Okay. Now, if a gate signal S2 at omega t equal to pi plus alpha is applied in negative half cycle, then let us consider then the gamma be the conduction angle, that will be beta minus alpha. So if alpha is greater than beta minus pi, when that will happen? If in the interval between pi to beta, when the source voltage is negative and the load current is still positive, S2 cannot be turned on because it is in the forward bias state. This is in forward bias. Okay. But the gate signal S2 must be delayed at least until the current in the S1 reaches omega t equal to beta. So on that period of time, you can write sine beta minus alpha equal to 0. So beta minus alpha is equal to pi. So my gamma equal to pi when alpha is equal to 0. Okay, that is at power factor unity. The power delivered to the load is continuously controllable between two extreme to the full source voltage and 0. Okay. Now in case of the three phase, we have three switch combinations here, and as we know that alpha can be either start from theta. So here the alpha is starting from theta. Here alpha is starting from 75 degree, and here alpha is starting from 120 degree. So based upon that, we'll have our output like this. Okay. So this is for the three-phase AC to AC cycloconverters. Okay. Next, we will study about the matrix converter. After this, if you have any doubt, you can ask. Okay. So now moving into the matrix converter. So matrix converter is a special type of AC to AC converter. This is also an AC to AC converter. Here the switches which are used for, this is my input which is an AC, we will also get an output at AC. But the switch which are used are basically bidirectional switch pairs. So it can be a diode bridge with a single IGBT like this. It can be a two anti-parallel IGBT with active diodes like this. It can be two anti-parallel NPT IGBTs. Okay, fine. So basically, in case of the matrix converter, we use some bidirectional switch combinations like this. This one is one, two, three, these are three switch pairs which we can use in place of this S1, S2, S3, S4, and we will get an AC to AC output. Okay. So this is an example of a direct matrix converter. This is three phase. So here we have 9 bidirectional switches. So the switching gate states. So the switching states will be 2 to the power 9, that is 512. Since we have 1, 2, 3, 4, 7, 8, 9. But not all of them can be useful employed. So regardless the control method used, the device of the matrix converter and switching state to be used must comply with two basic rules. One, we should have to take into the account that the converter is supplied by a voltage source and usually fed an inductive load. The input phases should never be short circuited and the output current should not be interrupted. Okay. The input phase should never be short circuited and the output current should not be interrupted. So for a practical point of view, these rules imply that one and only one bidirectional switch per output phase must be switched at any instant. So we must have to switch at any instant a bidirectional switch per output phase. Okay. So that by this constraint in a three-phase to three-phase matrix converter, 27 are the permitted switching combination. Instead of 512, by concerning these laws, we can have only 27 combinations. Okay. Here A, B, C are the input terminals. These are the input terminals. And these A, B, C capital are the output terminals. Fine. So this is an example of a direct matrix converter. So if you have any doubt, you can ask. Kindly note it down. I'm giving 5 minutes to note it down. Okay. So if you see the voltage diagram of a voltage source inverter and a matrix converter, so this is the diagram for a voltage source inverter. This is for a matrix converter. Okay. So here the output voltage wave from a matrix converter is shown to comparable with respect to the VSI. So the output voltage of the VSI can assume only two discrete fixed potential values, either this one or this one, right? But in case of the matrix converter, you can assume that the input voltage can either be, see in this curve, this is not considering one value, but it can be either A, B, C, D, whatever you can choose. So their value is not time invariant. So the effect of reduction of switching, so it will help to reduce the switching harmonics. Okay. Next, if you see the input current diagram and the harmonic spectrum here, this is for a 2 kilohertz. You will see that we have, this is our fundamental, we have our fundamental high. So can we see that the amplitude of the switching harmonic component, this ones, so amplitude of the switching harmonic components are lesser compared to the fundamental amplitude. So it is obvious because we are using, generally we use an input filter to reduce the harmonic distortion of the input line current. Okay. Another important feature of the matrix converter is that it can control the input power factor. So this is another important and attractive feature of matrix converter, which can only be held for some kind of control algorithms. So matrix converter can be controlled by various control algorithm, but in some case of some, most of the control algorithm that were proposed by the day, you can see that it has a feature of an input power factor control. Okay. Next, another category of this is, if you see that here from AC to AC converter can be of DC link energy storage. So VSI, CSI type of converter. So matrix converter can be of direct, that we already discussed. Another is indirect matrix converter. So indirect matrix converter can be sparse matrix converter, very sparse, inverting link matrix converter, ultra sparse. Okay. So these are the conventional circuit diagram for CMC, and this is for SMC, sparse matrix converter. This is for ultra sparse matrix converter. Okay. So and these are for inverting link matrix converter. Okay. So in that case, basically in case of the IMC type of converter, we basically use this kind of switch, and in case of the SMC type, we basically use this kind of switches. So that is what we are using in case of the indirect matrix converter. So basically we have two type of matrix converter. One is direct, another one is indirect matrix converter. Okay, fine. So what I said that we have two types of matrix converter. One is direct and another one is indirect matrix converter. So we discussed about the cycloconverter and matrix converter. So now if you have any doubt regarding of this, you can ask, and after which I will discuss a little bit about the sinusoidal, the space vector modulation technique, a little bit about the Clark and Park transformation, and then we will solve some questions that are related to the assignment of this week. Okay. Try to note this in your copy because this will help you all to solve the questions. Fine. So I'll discuss about space vector modulation. This is basically a technique. Uh, Before moving into space vector modulation, you should have to know a little bit about the Clark and Park transformation. So the Clark transformation basically uses three-phase currents. Like in the figure, if you see that we have IA, IB, and IC, right? So this is a three-phase current, and this current can be converted into a two-phase orthogonal stator axis currents I alpha and beta. So this is what we call the Clark transformation. Basically, these two currents are fixed coordinate stator phase with respect to the suppose one D component and one Q component. That is the direct component and the quadrature component. So this is DQ transformation, which is known as the Park transformation. I'm not going deep into the Clark and Park transformation. Okay. So this is the mathematical transformation form of Clark transformation. So it basically converts, as I said, a three-phase system to a two-phase orthogonal system. So if you have a IA, IB, IC are my three components. So it is basically converting this relation that IA should be equal to 2 by 3 IA minus 1 by 3 IB, IC. So it is converting this into two components, I beta and I alpha. So this is I alpha, this is I beta, and I naught, which is an homopolar component. In the IA, IB, IC is basically converted in terms of alpha and beta, which is my Clark transformation. Okay. Similarly, as I said, in case of the park transformation, we have an direct, another quadrature components. Okay. So here, what happens? The after transforming my three-phase component by means of a two phase components alpha beta, if we rotate it by a vector rotation over an angle, suppose theta, then this rotation theta can be done in two ways. One is direct, another one is quad. So we can convert this alpha beta in terms of dq. This is what we call, moving it into theta. If we convert it in terms of dq, it is called path transformation. So finally, if we relate this, we'll get a finalized relation as this. So try to note this transformation chart. This will help you all, because this is my park transformation, this is my inverse park transformation chart. So you can convert it by means of this. So this is my alpha beta ABC. ABC is basically converted into alpha beta, and alpha beta, by moving it by an angle of theta, we can able to make it in the axis of dq. What happens basically, we are getting an alpha beta like this. This is I alpha I beta, and we just rotate it. We just rotate it by an angle theta, and it will be giving you the dq component. So that is what the park and inverse park transformation is. Okay. So try to note this because it will help. So this is a topology of a two-level inverter. I'm discussing a little bit about the space vector modulation in by means of a two-level converter with RL load here. So this is basically a three-phase voltage source inverter. So the space vector modulation is basically an alternate method for the carrier based modulation technique that we had discussed in the last lecture. Carrier based modulation techniques, for example SPWM. Okay, so this is an alternative to this kind of technique, that is SVM method, that is space vector modulation technique. So this space vector modulation techniques basically operates in Clark referential frame, that is alpha beta frame. So that's why I discussed a little bit about the Clark and the Park transformation. Okay. So in alpha beta frame, if you see that the space vector, how it will works. So since we have switches like 1, 3, 5, 2, 6, 4 in this manner, right? So this is the state leg A and leg B and leg C. These are the combinations, and after which we'll get the output voltage as VA, VB, VC, like this. So after transforming it, we'll get this type of equation. So the space vectors are, there are 7 space vector with 0 to 1 to 7. So 0 to 7 we have 7 space vectors, and considering this vector, since we are doing the modulations, so that's why it is called space vector modulation. So we have 8 possible space vectors from starting from 0 to 7, because 1 to 7 7, 0 to 7 we have 8 possible combinations of state vectors. So these are, this V0 to V7 are called as by different name. So from these are all are state vectors. V0 and V7 are called zero space vector. Why? Because if you see from at V0 we have VA, VB, VC is 0, and at V7 also we have VA, VB, VC is 0. But in case of V1 to V6 that are not 0, so V1 to V6 are called non-zero space vector. So why we are discussing this? Because basically we use phase vector modulation, prefer to use in case of matrix converter. So these are the state. This is my optimal switching pattern. This is my suboptimal switching pattern. Okay. This is also my optimal and suboptimal for case of, this is my first case, second case. We have 6 case because we have 6 switches over here. So this is how the PWMs are applied into the switches. Either this case, these 6 cases. Okay. So the space vector modulation technique for 2-level inverter can be generalized for 3-level, 5-level, for various levels. So in case of the switching state, we can say that the in total the converter has 27 possible switching state, which is similar to the switching state as I discussed in case of the direct matrix converter. We said that in direct matrix converter we have for 3-phase we have 512 possible combinations, but out of which, by considering the law, we can have only 27 combinations. Okay. So this is what, why we are prefer to have SBM in case of matrix converter. So, and this is my representation in alpha beta plane. We generally draw this vector like this. This is an hexagon. Okay. So for a three level, we have more degrees of freedom since it has more space vector. So the diagram will be different, but it will be closest to this active and zero state of the vector. Okay. So we're not going deep into the SBM, just a brief review of it, and we discuss a cycloconverter and matrix converter. So now we will solve some problem that are related to the matrix converter and AC to AC converter, and that will helpful to your assignment. Try to answer if possible in the comment box. Okay. So first question, which of the following statement about matrix converter is true? It is used to convert AC to AC for amplitude. It is used to convert AC to AC for both amplitude and frequency. It can be used to convert DC to AC, used for AC to DC. Okay. So which of the following is the correct? Try to answer it. So here a matrix converter can convert both AC to AC for both the amplitude and frequency. Okay. So option B is correct. Next question, which of the following is not typically found in an indirect matrix converter? So in case of the indirect matrix converter, it doesn't require any kind of isolation transformers. Option D is correct. Which of the following topology is most suitable for application requiring modularity and scalability? Try to answer it. Okay, so cascaded HV multiple level inverter is the correct answer. Next, a single phase full wave AC voltage controller is given where R is given as 10 ohm, Vs is given as 120, okay, and frequency fundamental is 60 hertz considered. Alpha 1 equal to alpha 2 equal to alpha is given as pi by 2. So you have to determine the output voltage. So directly put the formula which I had given. So you can able to solve it. Okay. So try to solve it. Let me solve it. So I have Vs is equal to root 2 V is sine omega t. Just as I said in the formula that it will be the power factor cos phi will be 1 by pi minus alpha plus sine 2 alpha by 2 root over of. So we have posted the value. So since it is 5 by 2, so everything will be cut out. We have only 1 by 120 Vs by root 2. So 120 by root 2 is my answer. So 84.85 is the correct answer. Next question, in case of space vector modulation, why are zero vectors used in switching sequence? Why not only the non-zero vectors are used? So try to answer it. So in case of the space vector modulation, we use this zero sectored vector to for the reference with the sector to the center. Okay, so zero vectors in SVM are used to center the reference vector with the sector within the sector. Okay, so by applying zero vector, the average position of the reference vector is maintained closer to the desired location, allowing for better control of output voltage and reduce the harmonics. Okay, so main point is to center the reference vector. Next, what is the maximum achievable modulation index for a three-phase inverter without overmodulation? What is the maximum value? So the correct answer is 0.866. For a three-phase overmodulation region is 0.866 in case of SVM. Okay. Next, what is the primary reason for a SVM in three-phase inverter? Why we use SVM? For simplification of control algorithm, reduction in switching losses, maximization of the DC voltage, increased number of switch transitions. Which one is the correct? So it is used for maximization of the DC bus voltage. In case of SVM is used for maximum utilization of our DC bus voltage. Okay. Next, what is the significant advantage of direct matrix converter compared to AC to DC to AC converter? That means you have an AC stage, we have an inverter giving a rectifier, sorry, after which we have an inverter DC to AC, and then we have again AC to DC. We have an again rectifier. So why we are not using this? Because direct matrix control is simpler control strategy. It has a higher input factor, reduce switching losses, and smaller in size. Which one is the correct? Obviously, if we use a matrix converter direct, we have only one stage from AC to AC. You can able to convert it. So it is smaller in size due to absence of the bulky energy storage components. Okay. So what is the advantage of using an indirect over a direct? It's simpler switching scheme. It has higher efficiency, reduce switch harmonic distortion, capability to independently control input current. So which one is the correct? So it is preferred because it has a capability to independently control the input current and voltage, whereas in case of the direct matrix converter, it is not possible. Okay. The last question, in a Z source converter, what is the purpose of shoot through state? What is the purpose of shoot through state in case of a Z source type of converter? Okay. So basically, Z source type of power converter has unique impedance network to convert the electrical power, enabling a buck or boost step from a single stage. Okay. So that is why it is called a Z source type of converter, where we have inductor over here. This is my switch. Supply is here, and there used to be a diode, capacitor, a diode, capacitor. It will cross like this, and there is an inductor. So that is why it is called a Z source converter. So since the combination is like Z source. Okay, so this is a Z source converter. So it is basically used to boost the output voltage, not the shoot through state in a jet through converter. It allows both switches in a leg of the converter to be turned on simultaneously. So it basically helps to boost the output voltage. Okay. So that's all for the day. We have no more questions left. So if you have any doubt, you can ask. Otherwise, we'll leave the lecture here. Okay. Fine. So I hope you don't have any doubt. So next week we'll meet at Friday, the same time. Thank you very much. That's all for the day. Good night.